So we're going to be looking at what we call projectile. Folks, I'm starting. We're going to be looking at what we call projectile motion. Projectile motion is technically what Manav just tried unsuccessfully to do. Manav, I got the name wrong again. Jolly. Man, do it. But anyways, it was an unsuccessful projectile motion attempt. What we're saying for projectile motion is the object is still under the influence of gravity moving up and down, but it also has a horizontal component. Did I say component? Yeah. So a projectile is any object in free fall. We studied one-dimensional projectiles in Physics 11, stuff that was moving just up and down. But now that we've learned vectors, we can study two-dimensional projectiles. But first, we're going to start off with a thought experiment. Let's suppose Mr. Dewick has his Nerf dart gun, but it's supercharged. And he holds it horizontally, and then he pulls the trigger. Which of the following paths will the object trace out, the arrow trace out? We're going to ignore air resistance. So if I launch an object from my shoulder high horizontally, will it follow path A, path B, path C, or path D? Once again, we're going to vote. Once again, how high hold your hand up is how sure you are of the answer. So the four different options: path A, it goes straight down. Path B, it curves down. Path C, it goes straight for a while and then curves down. Or path D, it goes straight for a while, comes to a stop, and then falls straight down. Those are your four options. Question or a vote?
Question.
Yeah.
So D is just going straight and then cross.
Yeah. I'm just saying it's going to look like that if you think that's correct. Yeah.
So it depends on the velocity.
I don't know. We're going to find out. We're going to vote. How high you hold your hand up is how sure you are of the answer. Who says, Mr. Dewick, if you pull the trigger, it's going to be path A. It's just going to drop straight down.
How supercharged is it?
It's really irrelevant if I'm launching it from my shoulder, as long as it's leaving the barrel. Okay? Who says B? Who says C? Who says D? Why are all of you wrong? Why are all of you wrong? Doesn't depend at all. As soon as the bullet, as soon as the projectile leaves the barrel, what force is acting on it? Get the obvious one. Which way must it accelerate then? It's not going to travel straight for a while. You've been lied to by Hollywood. The correct answer is absolutely B. It does not travel straight for a while, and then gravity says, oh, ha, never saw you there. I better start acting on you and pulling you down. Hollywood has taught you that, by the way, because Hollywood has taught you that bullets go straight. Bullets don't go straight. You've all, I guarantee, seen the following scene. It's an action movie and there's a sniper. And so to build up drama, to show you some drama, they show the view through the sniper's scope, and you see the sniper has lined the X on the target. If that's all it took to be a sniper, any idiot could be a sniper. Oh, I can get the X on there. In real life, the targets are far enough away that the bullets are dropping a meter or more before they get to the target. And the snipers have to take into account how far the bullet's going to drop based on how much time it takes for the bullet to get there. In fact, for even further targets, the snipers have to take into account the curvature of the earth. But Hollywood has taught you that bullets go straight. Bullets do not go straight. As soon as they leave the barrel. So let's amp. You said, how big is this amped up? If this was an actual gun and we were firing it at a target, as soon as it leaves the barrel, the bullet starts to drop down. And it doesn't matter how much velocity there is. If there's barely any velocity, well, then it would look like that, but there would still be a sideways component. but it cannot be C, and it cannot be D. So where it says defend your answer,
-9 from 8.
gravity acts instantly. Okay? Gravity acts instantly. All right. Second thought puzzle. We're going to do the same experiment with a fairly high-powered Nerf dart gun, but at the same time as I pull the trigger, launching this one horizontally, I'm going to drop this arrow from exactly the same height vertically. Which one hits the ground first? Here are your options. Object A is going to hit the ground first because it's got a more direct path. Object 1. Object 2 is going to hit the ground first because it's got a velocity, so it's going to hit the ground first. Or they both hit at the same time. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So you got the argument. We're going to launch an object dead horizontal, and we're going to drop, let's make it an identical object. So you know what? Instead of Nerf dart guns, let's make them dense steel ball bearings so we really can, Spencer, ignore air resistance. Again, folks, I've seen 4 people on their phones. Put them away. This is the new physics stuff. Thank you. Let's vote. Who says, Mr. Duke? It's got to be object A, object 1, A, because it's going straight down. Shorter distance, it's going to hit the ground first. A. 1, 2, 3, 4, 5.
6.
Who says, no, object B has a faster velocity. It's going to hit the ground first. Who says B? B, number 2. B, object 2.
Actually, 8, 5, and 1.
You realize you had your chance, but your chance was here, my friend, because nobody went with that. You had your glory chance. They both hit at the same time. You know what? Let's run the experiment.
The blog. The Fortnite clip. The vignette.
So this is a fairly nice, from MIT experiment. They have some equipment that I don't have. This apparatus costs about $300, which I just can't justify. So what we have is a spring-loaded gun, and we're going to use 2 billiard balls, which are pretty dense. Pretty good, I think. Here's our setup. I'm going to prime the gun with the spring. One of the billiard balls has a hole through it, and when we pull the trigger, it's just going to drop straight down because that peg goes out from the middle of it. So that'll give us a pretty good vertical drop. The other one is sitting on a platform. It's going to get pounded sideways. So now, let's do them both at the same time. Let's do them both simultaneously. What's the correct answer? That's not the real question. Here's the real question. Why? Okay, what are the forces acting on them once they leave the gun? What are the forces acting on them?
Gravity, but they both have the same acceleration.
Okay, so they both have the same vertical acceleration, and they both travel the same vertical distance, and they both had an initial vertical velocity of 0. I know one was moving horizontally. Can you hear me using component language, by the way? Because I keep saying vertical, vertical, vertical. The key you want to bring here, Annika, is you need to realize when we look at projectiles, there's 2 motions going on, a horizontal motion and a vertical motion, and those 2 are completely independent of each other. I can look at one or the other or both, but they don't affect each other. Both of these are following the exact same vertical path with the same vertical velocity at the beginning, 0, and the same vertical acceleration, negative 9.8. Well, then, of course, t has to be the same. So, what this shows is that the horizontal and vertical motions of a projectile are independent. They don't even affect each other. What happens horizontally does not affect what happens vertically, and this is really the key idea. Both masses have the same vertical motion. Both of them traveled that path. So they have to hit the ground at the same time. Key idea number 1. First of all, what's the vertical acceleration of any projectile? You all know this from Physics 11. Negative 9.8. What's the horizontal projectile of any acceleration of any projectile? Catch. Once it leaves my hand, what's the horizontal acceleration of that? You ready? When it leaves my hand, you have to now imagine my hand is not here. I've just tossed it, so let's say it's right there. We freeze frame it. What are the forces acting on it? Okay. What else? Ignore air resistance. What else? No, my hand's not touching it anymore. What else? Inertia is not a force. What else? I'm waiting for somebody with conviction. Velocity is not a force. What else? Momentum's not a force. What else? There's an obvious answer that none of you are going for. Nothing. There is the only force that's acting on it once it leaves my hand, if we're ignoring air resistance, which we are, catch. The only force that's acting on it is gravity, which is in which direction?
Yeah.
So what's the horizontal force acting on it? It's a trick question. So if there's no force horizontally, what must the acceleration be? Ball back. That, Kiana, is the key idea that we're going to write in this box. The horizontal projection of the horizontal acceleration of any projectile is 0. But there's no way I'm writing out that much. I'm going to write this. That's a bad A. AX equals 0. In fact, we're going to sort of call that one of our physics no-brainers. When you give me a projectile to analyze, the first thing I'm going to write is AX equals 0. The second thing I'm going to write is AY equals negative 9.8, unless I'm not on the Earth. We're not dealing with that because that would be a changing acceleration. We can't deal with that. No. If we took a strobe action photo, turn the page, of a projectile, here's what you would notice. Let's suppose you took a picture every 1/10 of a second of an object that was launched from a cliff. You would notice every second its vertical distance was increasing. That's because vertically it's accelerating. But you would notice horizontally, the horizontal distance that it travels never changes. Why? Because the horizontal acceleration is 0.
All remaining gradients.
So this is the key idea, and it's not that intuitive. When you throw something, all of you want to think that there's a sideways force acting on it after it's left your hand. There isn't. The only force acting on it is the obvious one, gravity, which means horizontally no acceleration. So here's a little side picture here. It says, why is this? Vx is constant. Vy is changing. Why is Vy changing? Because there's a vertical acceleration. The biggest mistake kids are going to do is they're going to put the 9.8 into a horizontal equation because it creeps them out. There's no A. So yes, there is an A. It's just 0. A nice number to do math with. So why is Vx constant? Why does Vy change? Vx is constant because Ax equals 0. Vy equals changing because AY is negative 9.8. I can kind of do a simple experiment. If I walk at a constant speed and throw this straight up in the air, when it comes down, it will land in my hand. It won't land behind me, it won't land in front of me, and that's because it's going at a constant speed the same way I was. Now that's not very, very dynamic because it happens so quick. So again, MIT has a really nice piece of equipment that is far more expensive than I can afford.
How much?
This one's about 400 bucks. Actually, probably more. It's probably around 600 bucks because they got an electric sensor. So what we have is we have a little cannon, a golf ball cannon right there that's going to fire a golf ball straight up. It's on a rolling cart. There's the trigger. We're going to give it a push sideways. When it gets to the trigger, it'll fire the golf ball in the air. And if there is no horizontal acceleration, we should see the golf ball stay right above the cart and land right back on the cart, ignoring air resistance. And the golf ball should be pretty good. So it's a spring gun. Yeah?
OBJ?
Okay. No, that's physics. But it's not that intuitive to all of you because you keep, and this is what we went through last year, confusing velocity with force. They're very different. If it's a constant velocity, which it certainly seemed to be horizontally, what must your acceleration be if it's a constant velocity? Because the net force is 0. Let's watch that again in slow motion. Now, those of you that are looking really close might notice it actually ended up a tiny bit in front, and that's because you can't get it quite to fire at exactly 90 degrees. I'm betting it was like 89.9 or something. It's a really finicky device as well. To get it to come exactly back, that's actually why they put the funnel there, because there's just going to be some variation. Okay? So, example 4 says, consider the stop action picture of the projectile below. Along each path, indicate the velocity components. So it's launched at an angle. Did I say angle? Here's my two components. Horizontally, Vx looks like that. You know what Vx is going to be right here? The same. There's Vx. Draw it the same length as Vx down here. Eyeball it. You know what Vx is going to be right there? The same. There's Vx. Do you know what Vx is going to be right here? Spoiler alert. Write the Vx on top. You'll see why for a reason, not below. And you know what's going to be right here? Just before it hits the ground? The same. Why is that? Because there's no horizontal acceleration. The horizontal acceleration is 0. Is there a vertical acceleration? Okay, so what can you tell me about Vy in the second location? Bigger, smaller, or the same as when it left the ground? Someone said bigger, someone said smaller. The good news is one of them's right. Why smaller? You're right. Because as objects go up, what happens to their velocity? Slow down. That would be Vy. The resultant would be the tip to tail, but I'm not going to draw that in. Ooh, for a split second right there at the top, what would Vy be? 0. Now, does that mean the object has come to a stop? Still moving sideways. In fact, here, the resultant would be Vx because there is no Vi. This is one time you do know the resultant without doing any trig. It's just Vx. What about on the way down? Well, now it would be the same as on the way up, but negative. So I'll draw Vy about the same length as I drew it over here, because we're at the same height. Whatever we lost, we gained back. And when we hit the ground, Vy is going to be the same as when it left. In fact, the resultant, if this was 35 meters per second at a 60-degree angle, it's going to hit the ground at 35 meters per second, but at a 60-degree angle below the ground. Because what goes up must come down. Okay? Example 5 says, indicate velocity components on this stop action picture and then fill in the key facts. Oh, hang on. Did we answer the whole question? What is the velocity at the top of the path? Yeah, we answered that. What can be said about the projectile right when it's about to hit the ground? Same as the initial, but down. It says, indicate velocity components. So if you gave me the slanty, I guess Vx would be about like that, and Vy would be about like that. What about right there at the top?
0 for Vy.
Yep. And? So I'll eyeball it. Make your Vx the same as you drew it down below. Mine was about that long, so I'll draw it about that long. I can tell you at the top that Vy equals 0. I'll even make a little note there. What about when we get even with the launch again? Well, then it's going to look like this. There's Vx, still the same. Vy will be the same length as the one that I drew leaving the cliff. And in fact, the resultant would be the same as what it left the cliff at. What about just before impact? What is it not? It's not 0 when you hit the ground. It would be a really, really big velocity, something like this, but it would still be made up of Vx and just a larger Vy. Same Vx as before. Horizontal speed is constant. What's a good abbrev for horizontal speed? Vx. Why is horizontal speed constant? Because Ax is, yes. Vertical speed, a good abbrev for vertical speed is Vy. Well, vertical speed is changing because Ay is on the Earth. And then they are, you could say, separate, or I'll use a fancy schmancy word, independent. In fact, they're so independent, we're going to draw a line down the middle of our page. One side is going to be horizontal, one side is going to be vertical, and we're going to make sure we never cross over. The only thing that can cross over is a scalar, time. No, they're not. They're moving at a constant horizontal velocity. This is just the same as though they were at rest. The physics there is exactly the same as though they were at rest, because the only force acting on them is gravity, just like they were at rest.
But what if you like bounced up near the side?
Do you own a trampoline? I owned one growing up. Wasn't going to happen. I knew how to keep on a trampoline. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. What do I mean by example 7? Is there a cliff? Everybody say yes? Yeah. How are we launching the projectile? Horizontally. This is actually the easiest one. And on your test, there's going to be a horizontal projectile from a cliff. The next easiest is from the ground at an angle. Did I say angle? Okay. The toughest is from the cliff at an angle, and we'll get to that probably next class. But for now, what does example 7 want me to find? So the flight time, and then the range is the horizontal distance. So you can make a little note above the word range. That's the same as dx. All right. If last year, when we got to forces, a free body diagram was a good tool, if when we got to kinematics, we often used DFIC, if there is a projectile, which this is, the best tool I can give you is what I call a T-table. And what do I mean by a T-table? It's a table that looks like a big letter T. One side is going to be horizontal. One side is going to be vertical. And I always write down what I'm going to call my two physics no-brainers, because I can write these down for any projectile question. Even before I read the question, I can write down AX equals, everybody? AY equals negative 9.8. You might recall last year I told you we need three things to find the fourth. Now what I'm going to start to do, Logan, is carefully from the diagram or word problem, put stuff into these columns, and in one of these, vertical or horizontal, I'll know three things. And you know what I'm going to spend most of my time finding? You know what I'm going to spend most of my time finding? Time. Why is time so handy? Because it's a scalar, it can go in both. Got the approach? This is what we've been building up to. That 50, vertical or horizontal, but it's not 50.
Negative.
Why negative 50? Because we're ending up below from where we started. So we can say dy is negative 50. That gives me two things in that column. That 20, vertical or horizontal, that's a Vx. How many things do I know right now in the left-hand column? 2. How many in the right-hand column? 2. I need 3 to find the fourth, so I guess I can't solve this. Or can I? I know one more thing. Okay? These are the easiest mathematically, horizontally from the cliff. They're one of the toughest conceptually because there's something so obvious that you miss it. I know
0.
I'm going to be a little bit fussy though. I'm going to call that Vy initial since it's a changing velocity. Why didn't I bother putting an initial on Vx? What's my acceleration? Yeah, not changing, so I don't. Initial is final, it doesn't change. But my vertical velocity is going to change. Which column do I know two things in? Sorry, three things in. I'm going to solve this vertically. So now I'm going to make a little note here. T equals question mark. I know AY, DY, and VY initial. I'll rewrite those. Vy initial is 0, AY is negative 9.8, dy is negative 50. I'm looking for an equation that has a t, a vi, an a, and a d in it. You might want your formula sheet out because there is one. Logan, I think you're right. What? Or are you just trying to say it as long as possible to annoy me? Okay? Because you wasted our time. Vi is 0. So we can go straight to d equals at squared over 2. Now, technically, Spencer, who's not foolishly staring at his phone, technically, put your phone away. In your pocket. Thank you. Technically, this is a quadratic, but how many t's are there? I can get the t by itself without pulling out the quadratic formula. The reason cliffs at an angle are the toughest is it's a full quadratic equation to solve for time. Here, horizontally from a cliff, meh. How do we get the t by itself? Times the 2 over, divide the a square root. Or if you're someone, instead of dividing by 2, if you put a 0.5 in front, it would be divide by 0.5. On the bottom, you'd have a 0.58. I don't care which one you use. Now, if you missed the negative 50, which is an easy one to miss because most of you are used to going this way up, you would get an error on your calculator on this step. If you get an error on your calculator, usually that's nature tapping you on the shoulder, Rachel, to say, go check your vectors, please. Go check your negatives, check your directions. Don't just say, oh, I'll throw away the negative and keep going. Go find out where you zigged. 2 times negative 50 divided by negative 9.8 square root 3 point what? 3.19? I'll call that part A because that's the first thing they wanted me to find. What's the second thing they wanted me to find? Which distance? Horizontal distance. Okay, so now for B, I'm going to think horizontal. I'm going to go dx equals question mark, ax equals 0, vx was 20. That's only 2 things I need. I'm going to write time equals 3.19 seconds, but you know I'm using my answer button. Looking for an equation that's got a dx, an a, or sorry, a d, an a v, and a t in it. There is one, Logan. It's the same one. That's why I picked on you. Which equation? No, because this one's an even shorter version of the short version. Because what's A? What's A? So it's just going to be dx equals vxt. Stop. It's going to be 20 times 3.19. I get a horizontal range of 63.9 meters. Now, if I give this to you on a test, I probably won't say find the time and the range. I'll probably just say find the range and expect you to clue in you need to find the time. However, I can reverse this. In this question, I gave you the vertical displacement and I said find the horizontal displacement. I could also give you the horizontal displacement and say find the height of the cliff. To find the horizontal displacement, you would end up with 3 things in this column. You would find time horizontally, which is way easier because you'd be using this equation. How would you get the t by itself? It's not even a quadratic anymore. And then once you had time, you would walk the t into this equation, and that would give you your vertical displacement. So like I mentioned earlier, as far as I'm concerned, here I gave you the height and said find the range. You can now go backwards. If I give you the range, you can find the height. I like this question. Example 9. I'm not going to quite finish this before the tone goes. We're going to break this into chunks, but for now, you can certainly do question number 1, which is a bunch of different horizontal projectiles. They're all that diagram there. You can start that for homework, and we're going to add way more tomorrow. What is the block order tomorrow?
Second day, so we start with the
Sorry?
Start with you, fine.
Is it C to A, B? So I see you first thing tomorrow?
No, I'm stupid.
I don't know. There's an app for that.
It's fun here.
Okay? So we'll pause.